so we don't forget that as well. Okay, move this silly thing out of the way. There we go. All right, got everything. Yes, I did get an email about Status 17 today. So it looked like it had all kinds of fun new stuff in it. So, but I'm hoping that the university will upgrade. I don't know if I have to ask for that to happen or if it just magically happens, but we'll figure it out. So anyway, I have here the spreadsheet that we made for homework 4 last week. So these are the values that would be used to create the new predictor variables that go into the model to represent your passages of time in 3 distinct phases or epochs. So in terms of following example 6b, this homework does not follow it exactly. It's sort of, it's motivated by or like inspired by, but it's not like you can just pop my code over, hit find and replace 4 times and have it work like the last time. So we're gradually upping the level of sort of independence and thus difficulty. So there's, for instance, a model that has fixed slopes and random intercepts, and then you're adding in quadratic versions of the fixed slopes, keeping the random intercepts, and then in the next section you're to add the random effects. So it's a slightly different order that makes a little more sense in this context. But anyway, at the end of, I think it's section 2, is that correct? We're asking questions about whether or not the fixed effects of these slopes have adequately reproduced the saturated means. And so that was the set of questions I've answered via email that I wanted us to discuss as a group. So I need to get this all on one shot here. Okay. So in terms of which, I'm going to make a new column here for dummy question mark, meaning whether or not you would need a dummy code for that occasion to fully saturate the model. So at that point in the homework, you would have included a linear slope for the before phase, before the test, a linear slope, that's the only kind you can have, for relief 7 to 8. So if you tried to estimate a quadratic slope for this relief 7 to 8 phase, it's not going to work. And then a linear and a quadratic slope for the last phase here. So the tricky part to this setup is trying to figure out which sessions need to be dummy coded to fill in the holes, so to speak, to get back up to the saturated means. So I can tell you from a strategic point of view that this one and this one, session 7 and 8, can't be used. Because there is one difference between 7 and 8, and the model already has it. It's not going to be wrong. In contrast, if I go up to this point, there are 6 possible occasions that we're measuring change relative to 7 as the reference point here. How many fixed effects are in the model to describe change across those 6 occasions at this point? So this is homework 4, section 2 we're discussing. So the first model had linear change in all 3 sections. The next model asked you to add quadratic change to section 1 and section 3. So yeah, up to this point, there are 2 terms. There's a linear effect of change from 1 to 7 and a quadratic effect of change from 1 to 7. So if there's 6 occasions and I've spent 2, how many more do I need? You need 4. Does it matter which 4? I don't think so, so long as it's one of these 4. So like what I did is make dummy codes for those 4. Let me move this over so it looks a little easier to read. Okay. So then the other 2 potential parameters have already been saturated. This part we don't have to worry about. And now this part. So relative to 8 as a reference, there's 5 occasions. How many parameters have I spent to describe change across the 5 if I have linear and quadratic? I spent 2. How many are left? 3. Yeah, so 3 somewhere in here would be. So that's what I did. Now, what happens if you picked, say, 7 and 8 as ones that you added in here? Depends on your software. So what happened in Stata, for instance, is, so I tried this just to see what it would do. It kicked out the quadratic term. It gave precedence to the dummy codes and kicked out the fixed effects, which is not the same model. So you'll have to watch the output carefully to make sure that all of the terms that you added are actually being estimated. Otherwise, there's a redundancy in there that you need to investigate. Question, so you don't need anything from 7 to 8 because you spent 2 there already and there are only 2 occasions. Yes, more specifically, the intercept covers occasion 7 and the slope for 7 to 8 covers the 8. So one slope perfectly is going to cover those 2 means. So 7 to 8 is already saturated, is another way of saying that. Okay, so those of you who are working on this, does that help as a strategy? Okay. So yeah, you're saturating each piece distinctively in this case. That's the extra level of complexity. Any other homework questions while we're on the topic?
Can you say, sorry, when you say saturating each one separately?
Yes, bad phrasing. Each
Okay,
phase.
all right.
Saturating sort of this section of time and then saturating this section of time distinctively is what I meant. Okay. We have a question. Not sure how I can approach question 40. What is question 40? Can anyone tell me real quick? I don't have that open at the moment, I don't think. Enter the estimate for the instantaneous fixed linear rate of change at occasion 7. Oh, yeah, I love these ones. Yes, how do you approach it? Well, first off is to figure out which of these 3 slopes is active, so to speak, and relevant for that section of time. So in this case, we're talking about that section from 1 to 7 as being what's relevant. The other 2 are not yet relevant. So any estimate, Lincom, or contest 1D statement that you're using to generate instantaneous linear slopes would only have potential values for the slope that is active at this point. Now in this case, given the quadratic fixed slope that's included, what happens to the linear slope? So review of quadratic models. If I have time and time squared, the effect of time is specific to what? Time 0, yeah. So the linear slope is the instantaneous linear rate of change when time equals 0. Conveniently, session 7 is time 0. So the instantaneous linear slope at session 7 is actually given to you as a model parameter in this case, because that's where 0 is this time. Question from the audience. So it is active 1 to 7 and not 7 to 8 because 7 to 8 really would like turn on immediately after 7 ended. Yes. Can you do occasion 1 instead? Oh, yes, I can. So that one is a model implied parameter. So what's the rule about how the quadratic slope operates on the linear slope? What do we have to do to it to talk about how it changes the linear slope? Cough, cough, homework question. Do we cut it in half or multiply it by 2? Times 2. Yes, the quadratic coefficient that you get on your output is half the rate of acceleration or deceleration. To get to the full rate, you got to multiply it by 2. So twice is how the quadratic operates. So that means in writing an estimate statement, you would have the linear slope given a value of 1, because that's the thing you're trying to estimate, and then the accompanying quadratic slope moderates it. So you answered this question in a quiz. The last quiz asked you to estimate what the linear slope would be at time 4. Go back to your answer, and that will work the same way here. Just keep in mind what the value of the slope would be at that occasion as it is coded. So occasion 1 is -6 in this coding scheme. So that's what time is. That would have to be multiplied by 2. In terms of the others, I think I asked for 8 and 13 also. Same idea, just with a different variable, because this slope is no longer relevant here, and this one is also no longer relevant. Okay, does that help? Okay, I think I've caught up with the questions in the chat window. Nope, there's a new one. So for 8, it would be from 7 to 8. So the rate of change is discontinuous at 8. It jumps into a different trajectory at that point. So the slope from 7 to 8 gets you from 7 to 8. Because it's only a linear slope, there's no instantaneous needed. It just is the difference between 7 to 8. But the slope at 8 then is something that is already given, because that's when time 0 is in within that section of the trajectory. And in these cases, you could potentially change the coding scheme to directly give you what the slope is at occasion 13 or 1, but that would probably be more work. Sorry to be more confusing. Let me see if I can say this a different way. Like, occasion 8 to 13 is just this. Like, the others don't exist. They're not relevant. They covered the earlier parts of the trajectory. They're done. So the rate of change from 8 to 13 is governed exclusively by the linear and quadratic slopes of that third phase. Think of it as like the 4x1 relay at the Olympics. Did anyone run track in high school? Any sprinters here? A few people? I was on the long distance team. So the best I could do was like an 800-meter relay. But it's like in these models, the baton is being passed, right? Every time we have a slope shut off and the next one kicks in, it's like the baton's being passed. And now velocity is a function of the person who's now running with the baton, not the person who ran the last leg. So, all right. Other questions or things I can help with for this? Due next Monday. So got a few days to work on it. Office hours after class as usual this week. Okay, no? We're good for now? Good. All right, if you change your minds, let me know. Then I want to do the quiz next. So this is formative assessment number 5. I had a chance to look at all of your answers this morning, and there's a few things that I wanted to talk about. The first one here had lots of good answers, though. So in general here, the question, for what kinds of research designs would piecewise slopes models be useful? So I promised a few of you that I was going to call on you. Alfonso, do you have a microphone today? Or do you want to type? If he's listening.
I have a microphone.
Okay, what did you answer? Because I like this answer.
So I answered, so in behavior analysis, one of the common research methods or research designs is what's called an AB design. And in the A phase, you establish baseline. And so there is, you take data on one of the, on children and on some kind of task that you're interested in, for example, like washing hands. You want the kid to learn how to wash their hands independently. And so in the A phase, you just take baseline data. Then at some point you introduce the B phase, which is the intervention, and you do that for some period of time, and then you go back, what's called a reversal. You go back to the A phase, in which you remove the intervention and you see the effect of removing that intervention on the behavior, and then you introduce it again after some time to see the increase again, hopefully, in the behavior that you're interested in. And so it's like this 4-phased sort of research design.
Yeah, that's a perfect example, because the questions then would directly reflect how does the intercept and potentially the slope differ as a function of whether you're in an A phase or a B phase, as well as is it the first A phase or the second A phase? Because the thing that differentiates the first from the second is a maintenance potentially of the behavior that they've changed in B. And yes, Katie, I think you were thinking of that as well in your answer. Tasha, do you have a microphone today? I warned her too.
I do, but I'm actually driving, so
Okay.
I'm driving and listening. But if you want to share what I had,
I will do
go
that.
for it.
All right, you stay safe. There's enough divided attention already. So I think her example was looking at changes during the school year and then the summer effect. So kids do not come back to school right where they left off in May. There's always sort of a loss of learning over time as a function of whether it's the after a summer break. And so that kind of discontinuity could be characterized within these models. That was the one I remember. I think there was another one too. Does anyone else have ideas that you can think of? These sorts of designs. I can't remember who else was saying it, but there was more like pre versus post pandemic for various things. That one would be tricky.
Postnatal.
Say it again.
Pre and postnatal.
Pre and postnatal. Yep, that's an easy one, right? Baby in, baby out. Like that is a defined like moment in time that you can nail down. Pre versus post pandemic is trickier though, because like when did the pandemic start? Is okay, where did you live? At what point was your life personally affected? I know some of you had stopped coming to class, for instance, the moment all of these things happened, whereas the rest of us got ejected after spring break last year. Are you vaccinated yet? Is the pandemic over? Right? Do you get to go to Hy-Vee and not worry about things to do your browsing? So that one is a trickier because of the amorphous nature of the before and after, but for things where there's a clear-cut like change in circumstance, that's what these models are designed for. The way that I used it in example 6b was a much more data-driven, this looks like it should work if I break the trajectory in two pieces kind of thing, which would be harder to defend from a theoretical standpoint, but that model actually was the only one of the ones that was in chapter 6 that fit. So it was just a way to approximate a nonlinear trajectory, even if you didn't have a reason to put the knot there. There are models in which you can find the breakpoint. Those are latent change point models or latent knot models, and you can also have the breakpoint be random across individuals if you have enough data to estimate it. So, okay. Any other thoughts or questions on that one? Am I frozen? No, you're all frozen. Okay, there we go. Everyone's nodding. Good. Oh, synonym game, yes. List as many synonyms as you can think of for level 2 predictor. So I'm focusing not on what the predictor does, but just what you call it. So in this context of occasions nested in persons, what else could you call a level 2 predictor? Let's see the list of synonyms. You can either talk or type, whichever you prefer. Time invariant. Ding ding. Between. Between always works, just like level 2 always works, but between person, in this case, yes. Inter-individual, good one. Contextual. Yeah, that is less common in longitudinal. That would be more common in a persons and groups kind of scenario, but technically still correct. Person level, yep. per person, person characteristic, person level, all of those things. The idea is that it's measured once. So whether it does change over time, who knows? But you measured it once, you have to use it as time invariant. So yes, these are level 2 predictors. Their role in the model is a separate question that we'll get to, and I think that's number 4. Oh, this is it. This is one that I wanted to draw for. So how do multi-level models handle missing data? And so this question, several of you interpreted differently than what I had intended. So if you told me about ways of addressing missing data, such as full information, maximum likelihood, or multiple imputation, yes, those are things that one can do, but that is not what happens to predictor variables in particular in these packages, which is what I wanted to reinforce. So in a traditional multi-level package in which you have a single univariate outcome that is being predicted, such as in these programs, what happens to missing predictor data? How does the program handle it? Yeah, case-wise deletion. Rows have to be complete. Any row that is not complete gets bounced. So you can choose to let the program handle it, but then you run the risk of having a different sample across each permutation of a model where predictors would drop in or out, and thus cases might drop in or out. So to make your life easier, it may be useful to handle it a priori by selecting cases that are complete with respect to all the variables that are going to be part of your analysis. Thank you. Where's Angel reminded me in his answer, he actually typed in the code and said, I couldn't find where this was in R because I forgot to do it in R. So this morning I updated example 7b to include a function I found, complete dot cases, I think is a function in R that does the same thing. I'm sure there's 8 million functions in R that do the same thing, but this is the one that the Google told me about first. So, and I got it to work, which is the other criterion. If I can't get a function to work, I go back to the Google and ask for another one. That's my strategy thus far. So yeah, there is no FIML with respect to predictors, even though it is with respect to outcomes. This method of likelihood estimation is what's known as a conditional model, where the predictors are not in the likelihood. The likelihood operates on the residuals that are left over for the outcomes that have been predicted. And so the assumptions about the missingness mechanism, the benefit is really only with respect to not having to throw out a whole person. So if I have 3 out of 4 occasions worth of data, I get to keep the 3 occasions that I do have. That's the benefit. But if I have a time invariant level 2 predictor that's missing, do I still get to keep 3 out of the 4 occasions? If I have a level 2 predictor that's missing, what happens to that person's data? All of it. It goes to listwise deletion because all their rows are thus incomplete. So the program does nothing for you with respect to handling. It doesn't. So that's the benefit of switching to an estimation approach that is what's known as a joint likelihood, where the predictors have the same, how do I say this? They're treated as outcomes. Even though you can think of them as predictors and they can still predict things from a likelihood perspective, their characteristics in terms of their means, variances, and covariances are things that get found along with those of the outcome. And then the assumption is missing at random, which is conditional random. So I wanted to get out Paint to do a little brief discussion about that. So let's say that here's my y-axis, here's my x-axis, which is going to be time in this picture. And I have somebody who is currently in treatment for improving the rate of profanity that comes from their mouth. Let's say there's an intervention to stop people from saying things like shit so much. So maybe there's some, initial level of profanity here that they're at. They're trying to clean up their language. Maybe they don't want to teach their 5-year-old such phrases, or 6-year-old. Not that this is autobiographical in any way. Not that Huey didn't just watch Spaceballs the last 2 nights with us and learn all kinds of phrases. Every time someone said asshole, I gave his dad side eye, like, this is your fault. If he gets called from school because he called his friend an asshole at preschool, this is on you. Yeah, Spaceballs. Not appropriate for a kindergartner. Yes, Spaceballs. I did say Spaceballs. It's one of Jonathan's favorite movies. Would not recommend. But anyway, let's say that you're trying to improve someone's language and you get them to stop cussing so much. So they're up here. Based on your reinforcement, intervention, or whatever, they're down here. And then they don't come back. So what missing at random means is that the pattern of missingness like goes along with what would have happened. So like based on this trajectory, what if I estimate an intercept and a slope for this person that fits their values, it's like the trajectory would say that their missing data should be here, their missing data should be here. Like it should, like the function is the same, that you've accurately captured somebody's latent, and I hate to say that in this context, but like underlying like their rate of growth, and you just happen to be missing some of the points on it. That's the idea of missing at random. And that can be violated in several different ways. So what if I'm wrong? What if the reason that they stopped coming back is because they got tired of this and they wanted to have profanity license galore? So they start swearing again, right? Then this trajectory that we have is not a good representation of their underlying one. But this is a missing not at random situation. Like the values that they would have had were not predictable from the information that we do have for them. Now, where this can be potentially mitigated is with covariates. Let's say that we did have other people who completed the study and they had the same sort of pattern based on their age or their religion or whatnot. All these time invariant things that you might measure once have this pattern. So if I have somebody who didn't come back, right, this is all the data I have for them, but they're of the same religion, they're of a similar age, they're from a similar demographic profile as people that we know in reality went back up again, then including those covariates in the model then helps to condition like what is predicted for that person. So it's predicted based on their data that they have, but also the characteristics that go into the model. So there's something called auxiliary variables that you can add in certain packages that are not in the model per se, but they are supposed to be things that help you better account for missingness in terms of what the person would have had. That's not something that Mix does, but like in SEM packages, they often have that type of option. Yes, and fortunately Huey does not have older brothers to teach him how to swear, so it's all on us if he does get caught. But at least he'll say it properly. He's very good at using words in context. When he was 3, he was dealing with his sister and he said, "Damn it, sister!" And he calls her sister. He doesn't call her by her name because it's like mommy, daddy, and sister. And we're like, "Huey, where did you hear that word?" "From daddy. Because this one time I wasn't listening and so daddy said, 'Damn it, Huey.'" It's like, yeah, that happened. So, at random equals predictable. Yes, I think that is a good way to, it's that you have all of the information to make an inference as to what would have happened to those missing information. If you don't have enough information, then it's missing not at random, and everything you do will be some kind of wrong. So here's a reviewer 3 moment. Can you test whether your data are missing at random? What do you think? Reviewer 3 wants to know whether or not missing at random holds for your data as you've assumed. They want you to test for it. What do we say? So there's completely at random, which is what it sounds like, meaning that there's no reason why the missing data were missing. It's completely random. Then there is at random, which means predictably random, and then not at random, which means, yeah, I got nothing. We have 2 answers here. You can only test for MCAR, or you can compare groups. Both of those, I think, are getting at the same idea. There are tests for missing completely at random, but they're not really good. Because what you're doing is basically asking if the presence of a missing observation as a binary outcome is related to any of the stuff in your data set. And if it is, then it's not completely at random. It's at random. But it could be related to stuff that's not in your data set, and you don't have that information. So it's only a test that's based on the information that you have. But the fact of the matter is there is no way to test for missing at random because by definition you don't have the data needed for the test. So all you can do is argue. Dear Reviewer 3, missing at random is not empirically testable. However, by using full information maximum likelihood and including X, Y, and Z covariates that we think would be related to one's tendency not to return to the study, we hope to have satisfied our assumption as best as possible, or something like that. That's one of the few times when you can't say p less than 0.05 suck at Reviewer 3 as an answer. You have to articulate that you've thought about the missingness and anticipated the reasons for it. So in practice, like if you're doing a longitudinal study and say a child moves away from a school district and that's why you don't have data for their later observations, that goes in the model, right? A kid who didn't come back for reasons, that changes them from a kid who came back for reasons that are different based on what they would have done. So yes, at random means predictably random. That's what we believe. But in these models, if this person was missing the predictor here, here, or here, those data points are gone. It does not handle it. So your options for handling it include bringing the predictor into the likelihood by changing your software to be an SEM joint likelihood type of thing, such as in Levon, such as in M+, or multiple imputation, but that has to be done in a multi-level modeling framework. You can't just throw a standard level, single level imputation at it because the imputation has to understand that there are level 2 things and there are level 1 things, and it has to be able to anticipate random effects in addition to fixed effects as well as interaction terms. So missing data in multi-level models is an active area of research that people are continually trying to come up with new ways to fix it, because the truth is the predictors do not get handled, they get dropped. And I just felt all the caffeine crush into my bloodstream in like one fell swoop here. So I'm going to stop talking and say questions. Clearly, I was not meant to be an artist, but it works. Okay. Questions on any of that, for real? All right. Last one then. What are level 2 predictors for? So in specific, in growth curve models, I said, what kinds of fixed effects can level 2 predictors have? What do they do? This is what we're going to talk about today. So if I put in, say, a main effect, I put in a slope for a time invariant predictor into the model as a new fixed effect. What am I doing? Reducing the variance. A good answer, but not specific enough yet. Which variance? Modifying the intercept, yes. If I put in a fixed slope of a time invariant predictor, that is modifying the intercept. If I modify the intercept, can you guess which variance I should be accounting for? The random intercept variance specifically. If I put in an interaction of a time invariant predictor with time, then what am I doing? Modifying the slope variance, modifying the slope. Yeah, so you are modifying the slope So you're allowing the slope to change as a function of the time invariant predictor, thereby reducing the random time slope variance. So we'll talk about this today. Likewise, if we had a quadratic effect, you could have your predictor interact with time by time, which would change the rate of acceleration or deceleration as a function of the predictor and capture random quadratic variance. So more generally, the role of level 2 predictors is to moderate the level 1 growth curve. You end up with what's going to be a reference growth curve for the time invariant equals 0, and then you have different fixed effects that allow aspects of that curve to change. You start out higher or lower, change faster or slower, and what have you. That's what they are for. And if they matter, they reduce random effects variance that relates to that each term that they're modifying. So that's where we're starting today. Questions or comments on any of that? Okay. Want to see some equations? Said no one ever. But it is very helpful to see these, because if you can describe your model in words and provide your readers with an equation, then the people who hate equations can read your words and follow. The people who hate words can read your equations and follow, and you'll make everybody happy. So, for instance, Jonathan hates words. There was a story that we tell sometimes about how much he hates words. He opened up Craig Ender's Missing Data book, and he was looking for something, and he does this, like this, words, 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 words. Oh, looks at like this giant matrix equation for 30 seconds, or not even, like 3 seconds. Oh, okay, yeah, got it. And he's done, right? Whereas I typically read the words and skip the equation at first, and then maybe peek back at it if I'm feeling brave, right? So if you can communicate in words and in equations, this will help your reader understand what you're doing, and also offer a layer of transparency behind what was all in your model, as opposed to just the parts that you talked about because it was significant. So it is a useful thing. So I'm picking up on slide 14 of Lecture 7b, talking about time invariant predictors. I have an example here of a quadratic growth curve and the effect of time invariant years of education as a moderator of each aspect of the curve. So we started going through this last time, I believe. So pulling up slide 15. So we have quadratic growth over time. So it's a continuous nonlinear change model. And I have an intercept, I have a linear time slope, I have a quadratic time slope in my level 1 model. That means I've got each of those as an outcome in the level 2 model. So I think we did the first line last time. Does that sound right? Yes. So the intercept for each person starts off with a fixed intercept. So this is the anchor point for the whole model, the "you are here" sign. It is always the same thing. It's just the conditionality changes on what's in your model. So the definition of an intercept is the expected outcome when all your predictors are 0. Here, that means we're at the first occasion. So I have time centered at usuals where 0 is baseline. And it means we're talking about somebody with 12 years of education, because that's where education is equal to 0. So that kind of person starts out at whatever number gamma 0, 0 is estimated to be. Then the effect of education on the intercept is what you get if you just put in a main effect of education as a predictor in your model. So gamma 01 describes the change in the intercept for each additional year of education. So education moves your intercept up or down as a main effect. And in terms of the subscripts, this is gamma 01. The O is because we're predicting beta 0 for the intercept. The 1 is because this is the first predictor of the intercept. If I added a second predictor of the intercept, it would be O2, and then O3, O4, O5. And then likewise, U0 is because we're predicting beta 0, And this is now the deviation of each person's intercept from the one that is predicted by the model fixed effects. So after controlling for your education, how does your intercept differ from the one that's predicted for you? And to the extent that education matters, the variance of the U0s, our random intercept variance, should be lower after including education than before. Okay, with me so far? So this is where it gets a little tricky. Beta 1. Beta 1 is the linear rate of change. Because we also have a quadratic rate of change, beta 1 is the linear rate of change at time 0, specifically. So gamma 1O is the expected linear rate of change at time 0, but also given the role of education in this level 2 model, it's also conditional on education equals 12. So we have the linear slope for a high school educated person at time 0 is given by gamma 1O, and it's 1O because we're predicting beta 1. Then this thing right here in the middle, gamma 1, that is the first predictor of beta 1, so that's why it's 1. It is actually an interaction term. It's not obvious from the equation, but if you manually do the substitution in of all of these things for beta 1 and bring it up here, it interacts with time. And if that makes your head hurt in week 13 of the semester at 2:45 in the afternoon, I got your back. It's right here too. So on the next slide, I have the composite model that avoids the beta placeholders and just shows it to you straight. So this same equation that we're piecing through right now can be represented by the stuff in parentheses being each of the betas. So we have the fixed intercept, the main effect of education, the random intercept, then all three of these things each multiplied by time. So gamma 1 here in the middle is actually education by time in your syntax. That's how you get it. The effect of education on the linear slope is what gamma 1 is. Likewise, gamma 2 in the last line here predicting beta 2. Gamma 2 is the first predictor of beta 2. This is the effect of education on the quadratic time slope. So gamma 2 is actually a three-way interaction of education by time by time. That's how you would ask for it. So then the first fixed effect in each of these rows here, gamma 001020, you can think of that as like the reference growth curve. So we're used to thinking in regression type models as like having a reference group or a reference point. This is a reference curve. Gamma 10, or 00, 10, and 20 describe the expected rate of change for a high school graduate. Then each of these fixed effects of education modifies a specific aspect of the trajectory. 01 modifies the intercept, 11 modifies the linear slope, and 21 modifies the quadratic slope. The two-level equation version here also makes it helpful, is also helpful, I should say, to make it easier to figure out how to talk about our squares for the effect of these predictors. So I'm going to ask you 3 questions. Are you ready? We ready? Everyone awake? The answer to all 3 questions is the one in its line. Okay? The one in its line is the answer. So if I wanted to talk about the main effect of education and give an effect size for how much variance it accounts for, which variance is it? The one in its line. Random intercept variance. if I want to talk about how education by time, how much variance that accounts for, which variance is it? The one in its line. That one right here, what is that thing? Yeah, this is a representation of random linear time slope. The variance across people is what is being accounted for by education by time. Last one. If I want an R-square for education by time squared, which one? The one in its line. U2, random quadratic time slope variance. So these random effects here are logical prerequisites to the inclusion of time invariant predictors. The existence of individual differences of each kind, intercept, linear time slope, quadratic time slope here, then invites the analyst to say, okay, why are there individual differences? Is it because of how many years of education you have? Is it because of this other trait we've only measured for you one time? Anything that is measured once as a person level characteristic can predict individual differences. And there's 3 kinds of individual differences, and so there's 3 different ways that education can operate in this model. Okay, how are we doing? Yeah? She's like, it's 250, Lisa. It's not good.
This is,
Go ahead.
sorry, this is a silly question, but do we have to have the random intercepts for each of the betas if you have a fixed effect predictor there, or can you have a fixed effect predictor without those U's?
Oh my goodness, did you look at what's coming in the next slide?
Okay, no.
That was a perfect segue. I could not have done that any cleaner. The answer is it depends. So the idea of it accounts for the one in its line here. Pseudo R-square is one way to describe explained variance. So what one would do is start with a model that is unconditional. So like these equations on the left here, we would get how much random intercept variance is there to begin with, how much random time slope variance is there, how much random quadratic time slope variance is there, and then we would see how much is still there after controlling for education. And for each of these random effect variances, we would have a different R-square, where it is what it was from the model that didn't have the predictor minus what it is now versus what divided by what it was. So we'll get practice at interpreting each of these, but the role of each of these distinct fixed effects is different. Each is targeting a different aspect of individual differences via random effects. So your question then, Andrea, I think is this. What if you don't have any random effects? So this is actually pretty common. In studies that have relatively small level 2 sample sizes, they have relatively low power to detect random effects. So let's say that you are doing an intervention study. You're trying to reduce the rate of profanity in 6-year-old boys. And you go through your process, you measure their change over time, you start fitting these models, and you don't have a random time slope that's significant. You add a random time slope variance to your model, it doesn't result in a significant improvement, so you don't keep it. You go with a fixed slope model. Then, can you put predictors in? Can you answer your primary research question as to whether intervention reduced rates of profanity over time if people don't change differently over time? So that idea of not finding individual differences in the first place would lead to this model on the right here on slide 18. Is this okay? There are 2 different ways of looking at it. Some people say no, absolutely not. They say no because the standard error for any of the fixed effects in this model is only going to be correct to the extent that there really is no random variance here that's unaccounted for. because otherwise that extra variance component shows up in the numerator of the standard error. So if you don't have a random term here, you can potentially have standard errors that are too generous, p-values that are too lenient, and type 1 error rates up the wazoo. So they say no, can't do it. But then there's people like me that are like, but am I going to tell NIH that I can't do it just because I didn't find what I was looking for? That seems like a bad decision. So I would say yes, but you have to be reasonably sure that not having the random effect is not a type 2 error. Like, it really needs to be 0. And that is tricky to do. You're more likely to make a mistake if you have a smaller sample size. So if you are willing to say, yes, I'm still going to test these interaction terms, these cross-level interactions, even if there's no variance to predict, then that requires another layer of vocabulary to describe that situation. So I will say that this is still something that is controversial in multi-level modeling literature. There are classic textbooks that say, yeah, just make sure you test the random slope variance first. If it's not there, fine, you can go ahead. And other people that are like, no! But if you're willing to say, yes, go ahead, then we have a new vocabulary word. The new vocabulary word is systematically or non-randomly varying. It describes the idea that people need their own rate of change, effective time, deterministically as a function of predictor variables, but not randomly. So let's say that I have these situations. I'll describe what the language would be to interpret the findings. So let's say that I have a group by time, and I want to test whether or not my intervention group changes differently over time. And I do so in a model in which I do not have a random time slope. So it looks like this, right? No U here. If I were to find a significant group by time effect, I would then refer to the effective time as systematically varying. So what that would tell me is that I do not have individual differences in change, but that as a whole, one group changes differently on average from the other group. So it's an intermediary between the idea of a fixed slope, which is a constant, everybody gets the same slope, and random slope, which is a variable, a random variable, everybody gets their own. Systematically varying is like a compromise. It's not that everybody gets their own, but that different groups need different slopes. That's systematically varying. And so that's how I would talk about the effective time in this situation if I were to have a significant interaction term with group, but yet there's no random slope variance to go with it. So long as you test your random slope variance first, that's the key, prior to adding in the cross-level interaction. That's the most responsible way to go about this process. Okay. Does this make sense thus far? The idea that if I don't have a random slope in the model, if I test whether or not my time slope varies by group, then the way that I talk about my time slope is that it does vary by group, but not randomly otherwise. That's the idea. Sideways thumb still?
What would be the group in this situation? Because it just sounds like another like fixed effect predictor. If each group gets its own time, isn't that like each group has a fixed effect slope?
Yeah. Control versus treatment. I want to know if people in the treatment group change more. That's group by time.
But you don't call that like just another fixed effect predictor?
I do call that a fixed effect. I call it a cross-level interaction specifically because group would be a level 2 predictor and time would be a level 1 predictor.
Okay.
And so the language has to do with how I talk about the level 1 effective time at that point. Because if I don't have a random slope, it's not random. But it's not really fixed either because it varies by group. So I'd call it systematically varying. or non-randomly varying, either one of those. It's like Goldilocks and the Three Bears. This bed is too hard, this bed is too soft, this bed is just right. So it's not that people would need their own individual time slopes, it's that the control group changes differently on average than the intervention group does. 2 slopes instead of 1, but not, 30 or whatever number of participants you have. That to me seems like a reasonable thing to do. Second row here, different situation. Let's say that we go through our process of growth modeling, we test our fixed and random effects of time, and we do have random time slope. Individual differences in change. Okay, let's see how much of that is due to my intervention by putting in group by time as a new cross-level interaction fixed effect. But what happens is that the random slope variance for the effect of time goes away. That U1 was needed, but it's not anymore. Then in that case, if you take it out, then that is actually a victory, so to speak. What that would mean is that the only reason you previously thought people needed their own time slopes turned out to be because of group. And once you put group by time in the model, all the variance related to change over time is explained. You win. R squared 100%. So that's another systematically varying where you have a very strong effect of a predictor. That kind of thing can happen, particularly when you don't have a very large random slope variance. If there's not much to explain, it doesn't take much to explain it. If you had a random time slope to begin with, and it still had random variance left over, then the linear effect of time would just be called random at this point. Because yes, it varies by group, but it varies for other reasons that we don't know, so it's just random. One of the few instances in which random means what you would think it does. It's random, it's unexplained, I don't know. People need their own. It's not group though, because that's already in my model. So level 1 predictors then, you can describe them as fixed. Everybody gets the same slope. It is literally a constant. You can describe them as random. People need their own version of the slope. Or somewhere in between, people need different slopes as a function of a other set of predictors, but not randomly otherwise. That's systematically varying. Now the tricky part. Let me back that up, different word. How do I talk about R squared for these effects right here? Do you remember what the answer was before? The one in its line, right? Yeah, no. What do I do? Can't be a random intercept because this one does that one. What's left? Talk about effect sizes as CIs. You could do that, but what if reviewer 3 really wants an R squared? You can do it. The question is, where does it come from? What's left? What is another source of variability that's still in the model that's not on my slide? Residual variance at level 1. Yep, that's where it goes. T, that was a wonderful face. What? Yeah, no, that's where it goes. Let me back up here. Yeah, here's the combined equation. This is slide 16. Yeah, if there's none in its line, then all of these fixed effects, the only one that's left is E. So cross-level interactions, if the level 1 predictor that's in the interaction is not random, they explain level 1 residual variance instead. Yes, indeed. I have a slide for this, by the way, coming later, this idea of R square, because this is tricky. But yeah, E is what's left. It has to be E. E is also where the random slope variance would have come from in the first place, though. So from that perspective, it does make sense, even though it sounds a little crazy. This is actually a topic that I've been personally interested in from a research standpoint, and there is a paper that I am working to revise to resubmit looking at this issue, and I came up with a compromise in terms of when one should keep random slopes when you have small samples in which they may not have a lot of power. And in the simulation that I did, I figured out that if you use a metric of random slope reliability as your effect size for it, and you keep any random slope that is at least 20% reliable if you're using REML, or is it 15% reliable if you're using ML, that's right here, that was sufficient to reduce type 1 errors being inflated in the design. So this is just something that I have an idea. Like I said, this is going to be under review, not something you can quote yet, but this is a compromise potentially between including all possible random slopes and just using significance tests when you don't have a lot of power to detect them. So, an idea. Yeah. Okay, yeah, my thing is coming soon. But in the meantime, more equations. So what would it look like then if I had a second time invariant predictor to the same set of models is here on slide 21. So we have education and group as two different level 2 predictors. So the subscripts hopefully look a little bit more regularized now that you have more than one variable. The first subscript in each term in my equation for beta 0 is a 0 because I'm predicting beta 0. The first term in everything predicting beta 1 is a 1, and the first term in everything predicting beta 2 is a 2. From there, the second subscript says which predictor of that beta it is. So education is the first predictor of beta 0, group is the second. Education is the first predictor of beta 1, group is the second. Have any of you heard of terminology? It's often used in the context of HLM software particularly. Kelly, you just went to a workshop on this. You might have heard this term. The intercept of the slope and the slope of the intercept. Did any of the people use those words? No? I don't think so. Thank goodness. This is a term that needs to go away. But if you read research papers by people who use HLM software in particular, and I'm singling out this package because of the way the output is structured. So tables that people make when they use this software have terms in them like the intercept of the slope and the slope of the intercept. So I want to just very briefly describe what the hell that is. So of the refers to which beta. So like one way to think about the first fixed effect in each of these lines is as the reference point for what that term is going to be, in the same way that like beta 0 is the intercept of the overall equation, like gamma 00 is like the intercept of this beta 0, and gamma 10 is like the intercept of this beta 1, like as a jumping off point for what it will eventually become. So from that perspective, gamma 00 right here is the intercept of the intercept. Gamma 10 is the intercept of the slope, linear slope. Gamma 20 would be the intercept of the quadratic slope. I know that sounds crazy, but that's one way people talk about this. So like if slope is the concept that you're predicting, the intercept of the slope is just the fixed slope. Because that's what you would have if you had nothing else in the model, right? It has to be that as a minimum combination. So then these terms over here, gamma O1 and gamma O2, would be the slopes of the intercept, because they are slopes predicting beta 0. Whereas, wait for it, 1, 1, 1, 2, 2, 1, and 2, 2 would be the slopes of the slopes, because they are slopes predicting the time and time squared slopes. So I find that language very unhelpful and confusing. So I try not to use it. But in case you ever read a paper where they've used it, that's what the hell they're talking about. I find it easier to list these things in the way that they would be specified in SAS software or any linear model, right? So education, that's education by itself. Group, that's group by itself. Gamma 1, 1 here, that's education by time. Gamma 1, 2, that's group by time. 2, 1 is education by time squared, and 2, 2 is group by time squared. That's literally what I would do in my results section, just a list of fixed effects, and that's what they are. So that's what I would recommend anyway. Oh yeah, hey, this is the thing. Okay. I promised I had more slides on that, but I'm getting the general sense that maybe we're saturated for today. Have we saturated your means models, folks? Yes, a little. Yeah, I'm fairly saturated as well. Yeah. This is why this is not a 3-hour class. I gotta tell you though, it could be worse. For many summers, I taught workshops on these topics. 8 hours a day, 5 days for a week. Exactly. By 2 o'clock in the afternoon, there is not a single person listening to me at that point. They are all on Facebook, absent from the room, or on their phones. They're just done, right? But they paid good money for it, and I am contractually obligated to keep talking at them. That is the worst feeling. Oversaturated, exactly. Oversaturated, mental capacity under-identified, out of degrees of freedom and mental combination. So it could be worse. That is why I do not think workshops are nearly as effective as dosing this material in classes. And so I don't do them as much anymore, but it's a very strenuous experience. So yeah, could be worse. That's what I'm saying. Anyway, questions before we hang it up for the day? Got oversaturated now. Exactly. Yeah, we're full. You're just full. And just like your stomach being full, right, it takes time for it to empty out. And then you come back on Thursday and we'll be hungry again, and then we'll get full again, and the process continues. But in case you are not yet saturated and you want to talk about this anymore, office hours start now. Otherwise, I will see you Thursday. Thank you for coming. Peace out.